So we're going to spend a little time talking about some basic trigonometry. Most of these topics are in chapter 1 in the text, and so we will just hit some high points. There are some things more detailed that we'll need to go into later on, but just to have some basic pieces, just in case you haven't had a trigonometry course before, or if it's been a while since you've seen some of these topics. So we're going to start with the traditional mathematical perspective with the plus x to the right and plus y to the top, and talk about angles in degrees and radians. So one approach involves a unit circle. A unit circle is a circle that's centered at the origin and has radius 1. So the main points, the points on the axes, 1, 0 on the right-hand side, 0, 1, negative 1, 0, 0, negative 1 as we work our way around. This is called a unit circle. So in any circle, we can have the idea of an angle. And so we have the unit circle with a starting position that's pointing from the origin over to the rightmost point on the horizontal axis. And the angle then will rotate in a counterclockwise way to form whatever angle we're talking about. This angle is said to be in standard position when it's drawn in this way. So the starting position on the horizontal axis and then rotating upward. The angle then is measuring the amount of rotation. And so we had mentioned the idea that it's really rotating about another axis that's not the x or the y axis, in this case pointing into or out of the screen, and that's what we're actually rotating about. So in degrees, 360 degrees is one complete revolution about the circle. So 1 degree is 1/360th of a revolution. So you can imagine going all the way around the circle for 360 degrees. So 1 degree is not very big. There are historical reasons for the value of 360. We won't really get into those, but there are number systems and some different reasons for using 360. The historical reasons partially had to do with the number of days in a year in early calendars that were actually incorrect. But there are some other good reasons, and if you read in chapter 1, you'll see a couple of those mentioned. On the other hand, talking about radians, 2 pi radians is one complete revolution. So 360 degrees and 2 pi radians measure the same thing. So in this case, we want to ask, what does 1 radian actually represent? The idea of degrees and radians, then, since they represent just different ways of measuring the same thing, we can convert from one type of measure to the other using this relationship that 360 degrees is equal to 2 pi radians. So in thinking about 1 radian, if we have an angle that's not necessarily in standard position, it can be or not, 1 radian is a measurement between these, and this isn't to scale, but so 1 radian is a measurement between these, and it cuts off a portion of this circle. So the circle that we have drawn here, again, is still the unit circle that we started with originally, the unit circle, and 1 radian cuts off a portion of the circle. It's called an arc of the circle, and the arc that it cuts has length 1 unit. So 1 radian in a unit circle cuts off an arc of length 1. And that's the meaning of 1 radian. So what does that say about the circumference of a unit circle? If we start with an angle in standard position and go all the way around and there are 2 pi radians, then the amount that it cuts off, the length of that arc, which is the circumference of the circle, is 2 pi units all the way around. So the formula for circumference of a circle is 2 pi times the radius. The radius is 1 in this case, so the circumference of a unit circle is 2 pi units. If we have a circle whose radius is anything, including 1, but any radius r, and we're talking about some number of radians, we tend to use theta to describe a single angle if we have just one angle. So theta radians in a circle of radius r is going to cut off an arc of length r times theta. So if the radius is 1, then theta radians cuts off a length of theta. If it's a bigger circle, then that length will scale up or down according to the radius. If it's smaller than 1, then the r is part of that. If it's larger than 1, again, the r times theta is included. So the length of that arc formed by an angle of theta radians is r times theta. And so in the case of the arc that goes, or the angle that goes all the way around, the arc is the entire circumference of the circle, and that's the general formula, 2 pi times r. In terms of the basic trigonometric functions, we have, again, a unit circle that we're looking at, and just some arbitrary point selected that's on that circle. This point has coordinates, x and y, and it turns out that the trigonometric functions are defined in the context of cosine of the angle, again, the angle in standard position. The cosine of the angle is given by the x value, and the sine of the angle is given by the y value. If we switch the point somewhere else on the circle, the same relationship holds. The point can be anywhere in any one of the 4 quadrants, and x is equal to cosine of that angle. Again, it's the angle from in standard position. So the starting position horizontal on the x-axis, and then rotated around until the angle is pointing at the point on the circle. So go all the way around any of these 4 points. Again, any point that you have on the circle, but these 4 in particular. And we notice that the x value, that's the cosine value, never goes above 1 and never goes below -1. So cosine of an angle is always between -1 and 1. It could get there at those points, 0 radians or pi radians, or if we're talking about degrees, 0 degrees and 180 degrees. But those values of cosine always stay between -1 and 1. The sine is the y value, and again, the y value is always between -1 and 1. Some other things that we can see from here. The cosine of a negative angle, remember a negative angle means instead of rotating counterclockwise, you rotate clockwise. So for example, the x value of rotating to our point in the first quadrant is the same as the x value of rotating down to our corresponding point in the fourth quadrant. And so the cosine of negative theta is the same thing as cosine theta. For sine, notice that the y value was positive in the first quadrant and it's negative in the fourth quadrant. So sine of negative theta is negative sine of theta. And then there's some other things. If we look at what's 90 degrees away, or pi over 2 radians away, so pi over 2 minus the angle. Sine of that becomes the cosine of the original angle. Cosine corresponds to a sine of the original angle. So those are some things that you see in a trig class that we might use occasionally in terms of being able to convert from one of the trig functions to another. If our circle wasn't a unit circle, but it's a circle of radius r, then x is scaled again appropriately, so x is equal to r cosine theta, and if it's a unit circle, r is 1, and y is r sine theta. We could solve these differently to say, okay, well, let's solve for the cosine. So in that case, cosine theta is x over r, and sine of theta is y over r. Again, in all of these situations, cosine and sine are between -1 and 1, because the scaling, the biggest that x can be is r, in which case cosine theta would be r over r, and the smallest that x can be is -r, and so in that case cosine theta would be -r over r, which would be -1, and a corresponding idea on the vertical for the y values. So again, if you're not using a unit circle, it doesn't change anything about the sine and cosine. They're still between -1 and 1. All right, so in the unit circle, we have some other trig functions. There's tangent, and tangent is defined, tangent of an angle is defined to be sine of that angle divided by the cosine of that angle, which corresponds in the unit circle to the y value divided by the x value. Now, sine, cosine, and tangent are all functions, and really there should be tangent with parentheses around things and sine with parentheses around things. It's just not traditionally written in those ways. So sine, cosine, and tangent, as long as it's clear enough from what's going on, we don't write those parentheses. Although when we do this in Python, we will always include the parentheses because it's a Python function, and to give parameters, we need those parentheses. But when we're writing it down mathematically, we tend to not do that. So tangent is defined in terms of sine and cosine. There's another function called secant, which is the reciprocal of the cosine function. So secant of the angle is 1 divided by cosine of that angle. There's a cosecant, which is the reciprocal of the sine function. There's a cotangent, which is reciprocal of the tangent function, which means instead of sine of the angle divided by cosine of the angle, it's the other way around, cosine of the angle divided by the sine, which again, in terms of x's and y's, we could write all of these in terms of x's and y's as well. Secant would be 1 over x, cosecant would be 1 over y, and cotangent would be x divided by y. All right, so everything that you can do with a unit circle, you can also think of in terms of right triangles. We get a somewhat different approach, but it's exactly the same results. So if we have a right triangle, we have an angle, for instance, this angle. We have an x value and a y value, and we have a radius. And so sine of the angle is the opposite side divided by the hypotenuse. The hypotenuse is the side that's opposite the right angle, which is y over r. And that's exactly the same value that we had for sine of an angle in a circle of radius r. If we have a radius of 1, or excuse me, in this case, a hypotenuse of 1, then sine of the angle would just be the y value. Again, same as it was in the unit circle. Cosine is the adjacent value divided by the hypotenuse. Tangent is the opposite divided by the adjacent. So again, y divided by x. And we can do the same thing with secant, cosecant, and cotangent. They're just the reciprocals of those. So instead of opposite divided by hypotenuse, for cosecant, it's hypotenuse divided by the opposite. So sometimes you'll see trig presented from the unit circle approach, and sometimes you see it from the triangle approach. And usually in a trig course, you see both. Um, Depends on what you're doing, whether it's more appropriate to use triangles or to use circles. A lot of what we're going to be doing deals with rotation, and rotation works better with circles. There's a lot of connections then between the triangles and the circles where you can put both together. And so the Pythagorean theorem is a triangle relationship, and we can use that to prove some things about various trig identities. One thing, another comment, when we want the sine of an angle or cosine or any of the other trig functions of an angle squared, we tend to write that with the square beside the name of the function. So sine squared of theta would mean sine of theta times sine of theta. The Pythagorean theorem says that if you have a right triangle and you add the length of the shortest side squared plus the length of the middle length side squared, then you get the length of the hypotenuse squared. And so looking at that in terms of a unit circle and a triangle, we see that sine squared plus cosine squared is equal to 1, and that's one of the trig identities, a basic fact about sines and cosines. Sine squared plus cosine squared of a given angle is equal to 1. There are lots of other identities. You spend a lot of time in a trig class proving these different identities. For instance, what happens if you have sine of one angle plus another angle? Notice in this case, instead of having like theta and alpha or something, just switch to a and b. So sine of a plus b is sine of a times cosine of b plus cosine of a times sine of b. We're not going to prove that in this course, but we might need to use some of these things, some of these relationships. There's a corresponding kind of equation or a relationship, an identity for the difference between two angles. And if you're looking at cosine instead, or cosine of a minus b, there's some things that are really useful called double angle formulas. So what happens if you double the angle? If you double the angle, you don't just double the output. So sine of 2 theta is 2 sine theta cosine theta. And cosine of 2 theta can be written in multiple different ways. Cosine squared theta minus sine squared of theta is one of those. 2 cosine squared theta minus 1, or 1 minus 2 sine squared of theta. And again, there could be other ways we could write some of these things as well. But these are the traditional double angle formulas. There are corresponding half angle formulas and some other things as well. We talk about working with triangles then. So I have drawn some arbitrary kind of triangle, and talking about labeling it, we will usually label, when we're drawing this or writing this down, we will label it an angle with a capital letter, and then the side opposite that angle, we will use the corresponding lowercase letter to represent the length of that side. So given an angle of measure capital A, its opposite a side of length lowercase a. Do the same thing for angle B, and then the same thing for angle C. Now there's no preference in terms of which is A, B, and C. Sometimes we will go with the smallest angle as A, the mid-size angle as B, and the largest angle as C, but we can't always tell what those are just by looking. Or if we haven't actually drawn the triangle, we just have some idea that here are some angles and here are some sides. So there's no right way or wrong way, just consistently. Whatever angle A is, it's opposite side A. Angle B is opposite side B, and angle C is opposite side C. And so then when we talk about solving a triangle, we will have some of the information. Either we've been given some of the information, or we've calculated some of the information, or whatever we've needed to do. So we have some information, and we will try to find the rest of the missing pieces. Okay, so one approach for finding the rest of the missing pieces is called the law of sines. And it turns out that there's a relationship between sines of angles and the opposite side. And this correspondence is that sine of angle A divided by the length A is equal to sine of angle B divided by B and sine of angle C divided by C. So these three values are always the same if we have a triangle in this format. And so if we know some of the information, we can solve for the other pieces. So for instance, if I know angle A and say the side opposite angle A, so I know these two pieces, sine of A divided by A. If I know, say, the length B, then I know sine of A, I know that value, I know A, and I know lowercase b, I can solve that for sine of B. And then there are inverse functions that we can look at to undo that, and we can actually calculate what angle B is. Well, if we know sine of A, then we can calculate the size of angle A. Now we know sine B, so we can calculate the measure of angle B. From there, since there are, if we're thinking in terms of degrees, there's 180 degrees or pi radians in terms of the angles inside the triangle. Then we can calculate C, and from there we can find sine of C and determine the length of the other side. So with certain information, just a little bit of information about the triangle, we can calculate we can calculate all the pieces about the triangle. So that's one approach, law of sines. We have to know certain relationships, certain pieces, and with those certain pieces, we can find the rest of them. Another uh, set, and again, let's call it law of sines, but it comes from the things about the unit circle, the things about the way all of these are defined, and so on. There's also a law of cosines. Law of cosines says that a squared is equal to b squared plus c squared minus 2bc times cosine of a. So if you have, again, certain pieces of information, you can find the rest of it. This is when you happen to know things about two sides and the included angle. So if we know information about side B and side C, and we know what the angle is in between them, then we can solve the rest of the pieces. We can find out how long A is from here. We'll need to take a square root eventually, but we can find out the length of A. And then once we find the length of A, we can come back to the law of sines to find the other angles. So the law of cosines, if you notice, the first part of it kind of looks like the Pythagorean theorem, where you have the length of one side is equal to the other side squared plus the third side squared, but then there's this minus part here. And so it's very, well, the Pythagorean theorem is a special case of this. If the angle happens to be a right angle, then this last part becomes 0. And you get exactly the Pythagorean theorem from the law of cosines. But you don't have to have angle A and be looking for side A. There's corresponding things if you happen to have angle B or if you happen to have angle C. So you have two sides and the included angle in any of these three cases.